Hello, my name is William Garner. I'm going to talk to you about my ENME435 remote sensing project. The goal of this project was to construct a LiDAR scanner to scan an object on campus. Then we would create a 3D mesh of that object from our scans. The object I chose is the Testudo statue located in front of Gusset Hall. I chose this statue because one of my earliest memories of UMD is coming to Gusset Hall and rubbing Testudo's nose. Before we get too far into talking about the statue, let's first discuss what LiDAR even is and how it works. LiDAR, or light detection and ranging, is a type of active remote sensing process. It works by having a source emit a series of photons, which bounce off of the target and back towards the sensor. For this project, the source is the laser. These photons hit the target, the Testudo statue at Gusset Hall, and back towards the receiver, which is the Raspberry Pi 2 camera. These photons do not hit the camera directly in the center, instead lying somewhere along the focal plane of the camera. In order to calculate the distance, we need to first find the angle at which the light hits the focal plane. To do this, we require the pixels from center, or the distance from the center of the focal plane to the spot where the photons hit. And we also need the radians per pixel pitch, which is the radians in between each pixel, and the radian offset, which is going to account for any errors during the alignment process. Now, once we have these values, which we'll go over in the calibration section, we will be able to find the angle at which the photons hit the focal plane by multiplying the number of pixels from the center of the focal plane by the radians per pixel pitch, and then adding that radian offset, again to account for any errors. From here, we know the distance between the camera and the laser, as this is set to 12 inches by the mounting setup that I have put together. And from there, we can set up a right triangle and use trigonometry to calculate the distance between the target and the LiDAR setup. The radians per pixel pitch and the radian offset were both unknown for my setup at the beginning. In order to find these, I first ran a Python script to help me rotate my laser so that the beam was in line with the camera. Then I began taking a series of photos starting at the wall and moving backwards 6 inches at a time until I reached 10 feet. I then used a Python script to perform the distance calculations mentioned earlier to compare my actual measurements to the distances at which they should have been taken at. Using this data, I was able to edit my radian offset and the radians per pixel pitch values to get my measured distances to match theoretical ones. With these values finally determined, I could make my way to the statue. Alright, now let's talk about the statue. I thought that Testudo would be interesting to scan due to the amount of detail it has. Not only are there channels to form the pattern of its shell, but its limbs have a lot of definition thanks to the scales carved into it. Additionally, Testudo's face has details as well, including its mouth and its eyes. I was very curious to see how my scans would represent these details. Now, I know that was a lot of talking, and we are all very eager to start scanning the statue, but there are some issues we need to solve first. As you can tell by the photos, it is surprisingly bright outside Gusset Hall. Even well past midnight, the lights from the football stadium and from the building itself were bright enough to mostly illuminate the statue. This would prove to be an issue in earlier attempts at scanning, as it was too bright to see the laser at some points. In order to block out some of the light, I recruited a willing volunteer to hold a blanket up in front of the Gusset Hall lights, allowing for a better capture of the laser in my photos. Thank you to Shannon for the help. Another issue I had was the height of my tripod. Even fully extended, the tripod did not make it above the base of the statue, the result of which being my early scans of Testudo completely missing her legs. In order to get a better view of Testudo's legs, I decided to further elevate my LiDAR scanner by putting it on top of a folding chair. With these issues solved, I was finally able to start scanning. So, as you can see, this is the process of me completing one of the scans, in this case for the left side of this Testudo statue. The mount is on top of the tripod, which is in turn on top of the chair, just to get a better elevation. And what I'm doing is I'm taking an image and then slightly tilting the whole mount upwards to get a different angle and taking another image. I'm repeating this process for the whole statue. Okay, so here are some of the images generated from my scans. This is of the right side of Testudo, and as you can see, the red laser is fairly clear in most of the photos. Even going towards the ones at the top, it is a little difficult to see in this one, but I ended up using the color picker Python script to find thresholds that would allow for that laser to be picked up in my data generation script. This did result in a lot of noise, but I was able to edit that out eventually. Okay, so after generating a .txt file for each set of photos detailing coordinates for the points, I imported those coordinates, those files into a MATLAB code and began to filter them. So this code, using a bit of trial and error, just takes all of the points that we want to keep in our point cloud and then assigns them to a different, now cleaned up array. So then, again, using trial and error, I perform some transformations and some translations of those point clouds in order to get them all to fit. The final result of running this code is this point cloud of Testudo. All right, now finally we can begin creating our mesh. Upon importing our point cloud into MeshLab, this is what we get. Of course, this can be cleaned up a little bit just by removing some of these excess points around the statue. So after cleaning up the mesh, we can begin to apply the computing the normals for each point. Now I ended up with a value of 81 during my testing. That seemed to work well enough for me, so that's what I'm going to use here. As you can see, all the yellow is facing the outside, which means the normals are all facing towards the outside of the figure. And then we can go back into filters, into the remeshing, and then down to the screen Poisson to create our mesh.